Hi, everybody. Let's see. So what I want to do today is talk about a topic called Gaussian Quadrature, which is an alternate way of estimating values of integrals. Okay, let me start off with a simple example. Actually, I'm not going to start off, strictly speaking, not with Gaussian Quadrature, but with a very similar idea. I'm going to look at Simpson's rule more carefully and from a different perspective. Now let's consider this integral. So the integral from 1 to 7 of 4 minus x squared. So this is a simple uh, parabola that opens down, right? So it looks something like this, right? It'll be the black curve in this diagram, simple parabola that opens down. Let me come back to the picture later. We can compute this integral exactly using Simpson's rule. Remember that Simpson's rule is based on a quadratic interpolation of the given function. If we start off with a quadratic function, of course, Simpson's rule will work perfectly. It'll give us the exact value. In fact, as we saw, it even works perfectly for cubic polynomials, which wasn't obvious at first, but that's true. So we can compute this using Simpson's rule. Moreover, we don't have to subdivide the interval from 1 to 7 up into thousands and thousands of subintervals, right? We only have to divide it up minimally. We only need really 2 subintervals. So that's what I'm going to do. I'm going to divide it up into 2 subintervals, one from 1 to 4, and the other one from 4 to 7, so that both of them will have a width of 3, right? So 2 subintervals, each of width 3, going from 1 to 7. And then the rule for Simpson's rule was that you take h over 3 times the value at the left endpoint plus 4 times the value at the midpoint plus the value at the right endpoint. And if you do this for this particular function, right, the left endpoint, let me see. Actually, first of all, the value of h is 3, so the coefficient out front cancels completely. And we get the f of 1, which would be 3. 4 times f of 4 would be 4 times negative 12. And f of 7 is going to be negative 45. And you add it all up, and you get the final answer, negative 90. And, of course, you can check that by integrating it the old-fashioned way, symbolically, as I taught you to do in calculus. And you'll get the same answer of negative 90. OK, now let's go back over here. This formula... I'm going to rewrite it slightly. So Simpson's rule said that it's basically this form, right? H over 3 times a sum of some sample points where the midpoint is weighted more heavily. I'm going to rewrite it this way, which is, I think, is a nice way to think about the rule. What we do is we take the length of the interval, which is b minus a, and we multiply that by this guy, which you can think of as a weighted average of the values of the function inside the interval. So we sampled it at the left endpoint, at the midpoint, and at the right endpoint, and we took the weighted average of those 3 points, right? So the first point is weighted once, and the second midpoint is weighted 4 times, and the right point is weighted once, and then we divided everything by 6. To get the overall weighted average of the values at those 3 points, and then we multiplied by the length of the interval. So we can think this is the length of the interval times a kind of average value of the function on the interval, right? And as it turns out, if you compute the average value in just this way, it will give you an average value that works perfectly for computing the integral of the function over that interval. Right? As long as, with the qualification, let me remind you that f is a polynomial of degree no more than 3. Right? Then this will work perfectly. And one way you can think about that is that we've taken this function, again, the parabola from the previous example, the parabola opening down. We sampled it at these 3 points, at the left endpoint, at the midpoint, and at the right endpoint. Right? We sampled the function there, and then we imagined that instead of being a parabola, that the function was actually a step function, and that the first step has height equal to the height at the left endpoint. The middle step, which is the widest, has height equal to the height at the midpoint, and the last segment has height equal to the height at the right endpoint, right? So we replaced this parabolic area, the area under the parabola, with the area inside three rectangles. And it turns out if we do it in just this way, so that the length of the left rectangle is relatively speaking is 1, and the relative length of the right rectangle is 1, and the relative length of the middle rectangle is 4, right? So 1 to 4 to 1 ratio. Then the area under the rectangles is exactly the same as the area under the parabola. And that's why it's called quadrature. That's how we get this weird name, Gaussian quadrature. Quadrature meaning that we take a curvy area and we change it into a kind of rectangular area, or an area with right angles, or that's easy to calculate. Okay, now in this case, what we did was we saw that for a polynomial up to degree 3, we can simply sample the polynomial at 3 points inside the interval and take a weighted average of those 3 points, and that's good enough to get the integral. But we can actually do slightly better. As it turns out, it's possible to do it by just sampling the function at 2 points inside the interval. So let me show you that. Now here are the 2 points I'm going to use. Well, let me explain this first of all. So we're going to set this up. I'm going to say that I'm going to use the letter m to represent the midpoint of the interval, so a plus b over 2, and I'm going to use the variable r to represent the kind of the radius of the interval. It's the difference from, or the distance from the midpoint to each of the endpoints. So, or in other words, it's half of the length of the interval. In the particular case of the example we were just doing, the midpoint was 4 and the radius was 3. Okay, and then the rule says that what we do is we sample the midpoint at these, we sample the function at these 2 points, at the point m minus r over radical 3 and at the point m plus r over radical 3. So at those 2 points, one on each side of the midpoint, actually symmetrically distributed about the midpoint. In the example we were just looking at, we could sample the function at the points 4 plus or minus radical 3. Because if r is 3, then 3 over radical 3 just reduces to radical 3. Right? So those would be the 2 points at which we'll sample the function. Let's try it out, shall we? So here's the formula. Let me give you the formula first, then we'll try it out. The formula says that what we do is we take the length of the interval. Ooh, I did it again. So what we're going to do is we're going to take the length of the interval, b minus a, and then we're going to measure, multiply by the mean of the value of the function at those 2 points. So we weight each of those 2 points equally. We just take the average of those 2 points, and we're going to let that represent the average height of the function on the interval. And if we do that, I claim that we're actually going to get the correct value for the area of the under the curve. Let's try it out. So in our particular case, let's see, what do we got here? The length of the interval is 6, right? And then we're going to take the value of the function at 4 minus radical 3. So I plugged 4 minus radical 3 into the function. Remember, the function was 4 minus x squared. So this is 4 minus the x value squared. And then we also plug it into the other test point at 4 plus radical 3. 4 plus radical 3, we plug that one in, and then the value of the function is 4 minus the other test point squared. Take the average of those 2 y values, those 2 values of the function, you get some cancellations. If you add everything up, it reduces to this, and you actually end up with negative 90, which is the same thing we got before, right? That's comforting. So that's not a coincidence. In fact, just by sampling any polynomial of degree up to 3, assuming you're working with a low degree polynomial like that, then if you simply sample it at these 2 points, here, that'll be enough to give you an average value of the function, which is adequate for calculating the integral of the function on the interval. Okay, so that's rather remarkable. Right? Only have to sample the function at 2 points to determine the value of the integral, as long as it's a cubic polynomial or smaller. Now, why is that, right? Oh, by the way, so here's the general formula we could say, right? The value of the integral is the length of the interval times the average of the function sampled at those 2 points, m minus r over radical 3 and m plus r over radical 3. Okay, now that it'll work for any f representing a polynomial of degree less than or equal to 3. Why is that true, though? Well, the theory is based on the Legendre polynomials that we talked about in the last chapter. So recall that the degree 2 Legendre polynomial was some multiple of a constant multiple of 3x squared minus 1. I don't really care about the k. You have to adjust k in order to be sure that the Legendre polynomial has magnitude 1. Remember, in Legendre theory, we were thinking of the polynomials as being vectors, and we wanted to normalize them so that they had magnitude 1. That doesn't matter in the current context. I don't care about the magnitude. Actually, all I care about is what the roots of this polynomial are. So if you're looking at this polynomial, the roots are here, right? The roots are going to be plus or minus 1 over radical 3. The k doesn't matter. So this is where this number 1 over radical 3 comes from that we saw, that you see up here, right? R over radical 3. Turns out they correspond to the roots of the Legendre polynomial. Okay, so now let me try to set this up, and I'll show you why the formula was correct. So first of all, what I'm going to do is I'm going to assume, as before, that f is any polynomial of degree no greater than 3. And then let's define function g to be the linear interpolation of f, where we interpolate at the 2 sample points indicated at the roots of the Legendre polynomial at plus or minus 1 over radical 3. By the way, now that we're doing Legendre theory, we're going to be focusing on the interval from -1 to 1. So I'm sorry, I should have mentioned that. We're assuming for the moment that a is -1 and b is 1, right? That our integral is from -1 to 1. Then, okay, so we sample the function f at these 2 points, plus or minus 1 over radical 3, and form the linear function that passes through those 2 points, right? So g is the linear interpolation of f at those 2 points. Now, here's a picture of g, right? You could say that g is the blue line, right? The 2 pink points, this is the sample of f at -1 over radical 3, and this is the sample of f at +1 over radical 3. So we sampled the function at those 2 points, and then we drew the straight line that connects them, and that straight line is g. And what we're going to claim is that finding the area under g from -1 to 1 will give us the same value as the area under the original function f from -1 to 1. Okay, now, first of all, let's just get the formula for the integral of g. So if we integrate g from -1 to 1, well, it's quite easy to integrate a linear function on any domain. For a linear function, the integral over a given domain is just going to be equal to the length of the domain times the average value of the function, and the average value of the function is the value that the linear function takes right at the middle. Or, equivalently, you could take the average value of any 2 points that are symmetrically situated about the center of the interval. So, for example, by taking the average value of these 2 points, we get the average value of the function. And I've represented the average value of the function here by the black horizontal line, right? That represents the average value of the function. So this integral of g from -1 to 1 will be equal to let me do that again. It'll be equal to the length of the interval times the average value of g. And the average value of g will be the same thing as the average value of g at these 2 points. I mean, it's a linear function. As long as you sample at any 2 points symmetric about the origin, you'll get the same mean value. You could simplify this, cancel the 2's, and write it this way. Actually, I kind of like this better, so I'm going to think of it that way. Length of the interval times the average value of g at the 2 sample points. Okay. Now this looks a lot like the formula for the general formula for the integral that I showed you here, right? This guy. It's exactly the same form. The length of the interval times the average value of the function at the two sample points. What I have not yet done is proven to you that this integral is in fact the same as the integral of f. So that's what I'm going to do now. Now let me introduce a function h, which is the difference between the original function f and its linear interpolation. Right? So h is f minus g. That means you can rewrite f as the sum of g plus h. Right? In a sense, we're decomposing f into a linear part, which is g, and a cubic part, or maybe polynomial of higher degree up to cube, which is h. Notice that h does have to be a polynomial because f and g are polynomials, and because f and g, well, let's see, g is linear, f has degree no greater than 3. That means h also is a polynomial of no greater degree than 3. And that's important. So h is a polynomial of degree no greater than 3. Now, what happens when you evaluate the original integral of f, right? The original function from -1 to 1. Well, because f can be decomposed into the sum of g plus h, therefore its integral can also be decomposed into the sum of the integral of g and the integral of h. And what I'm going to show you is that this integral of h turns out to be 0. Okay, which is not so obvious, but it turns out to be true. This second integral turns out to be 0, and that means that that'll verify that in fact the integral of f is the same as the integral of g, and so that this formula that we used can be used to evaluate the integral of the original function. Okay, now why is the integral of h equal to 0? We have to go back to the theory of Legendre polynomials again. So remember I said that we know that h is a polynomial of degree less than or equal to 3. Another thing we know about h, because h was defined this way as the difference between f and g, and we know g matches f at those two sample points, plus or minus 1 over radical 3, that means that h, in fact, must have zeros at plus or minus 1 over radical 3. Well, you know that if a polynomial has zeros, has known zeros, you can factor the polynomial using those roots, right? So this has roots of -1 over radical 3 and 1 over radical 3. That means h can be you can factor those two terms out. Now, of course, -1 over radical 3 and +1 over radical 3 were also roots of the Legendre polynomial of degree 2. So that can also be factored in the same way. That means that the Legendre polynomial looks pretty much like part of the, two of the factors of the polynomial h, right? So these two factors, x plus 1 over radical 3 and x minus 1 over radical 3, they're going to be factors of h. And remember, k is just a real number. So h may have one extra monomial factor, may have one extra root, or may have no extra roots, depending on whether the degree is 2 or whether the degree is 2 or 3. But in any case, what this means is that we can factor h into a product of L2 plus some other polynomial. And this second polynomial, I've denoted it q for quotient, right? So it's like we took h, we divided by L2, and the quotient was q. And notice that h is divided evenly by L2, so there's no remainder, right? H is exactly equal to L2 times q. In that case, let's see, what we know is that q is also a polynomial, and its degree can be no greater than 1, right? So q is a polynomial whose degree is no greater than 1. It's at most linear. It might just be a constant, right? But now here's the thing. Remember the whole idea of Legendre polynomials was that they were orthogonal to each other, right? So that each Legendre polynomial was orthogonal to all the earlier ones, and all the later ones, of course, implicitly. And that means that, in particular, that each Legendre polynomial, like L2, is actually orthogonal to all polynomials of lower degree, right? So that was another fun fact about Legendre polynomials. Legendre polynomial of degree 2 was orthogonal to all polynomials of lower degree, and that means in particular that L2 is orthogonal to Q, right? These must actually be orthogonal polynomials. So what does that mean? That means that when we try to integrate h, right, integrate h from -1 to 1, well, again, we can write h in terms of its factors. It's L2 times Q. This formula here, where you integrate the product of two polynomials, this is exactly how we define the dot product, right? The inner product in the space of polynomials. This is the dot product between L2 and Q. So that integral is L2 dotted with Q. And because they're orthogonal, that dot product is 0. And therefore, the integral of h is actually equal to 0! Exclamation point. Yeah. So integral of h over this interval is actually 0. So that verifies that, in fact, the integral of f is the same as the integral of g. And so to summarize, for any polynomial of degree less than or equal to 3, its integral on the domain from -1 to 1 is equal to the integral of the linear interpolation at those two sample points, right? That the linear function has the same integral as the original function. Okay. Okay, so and then another way to summarize it is now we can say that therefore the integral of f is equal to the integral of g, and the integral of g we computed earlier was this. It was the length of the interval times the average value of g at those 2 points. And finally, notice that because g copies the values of f at these 2 points, right? That's how we form the linear interpolation g. We copied the value of f at these 2 points. We could equally well have written f here instead of g, right? F for g in both of these places. So this gives us a formula for evaluating the integral of a function without actually doing any calculus, right? You just, as long as it's a low degree polynomial, no greater than cubic, we just sample the value of the function at these 2 points and average them and multiply by the length of the interval. And in fact, that formula generalizes very nicely. It generalizes to this formula where we say we multiply the length of the interval times the average value of the function, where it's been evaluated at 2 sample points. One point is at the midpoint minus r over radical 3, and the other sample point is at the midpoint plus r over radical 3. As long as we sample the original function at those 2 points and average them, that'll be a valid average that we can use to compute the integral by just multiplying by the length of the interval, right? Okay, let's try it out. Let's, well, I'm sorry, before we try it out, let me, we kind of did try it out, didn't we? Because I did some examples earlier, but first let me generalize it, and then I'll do some more examples. You can see how you could do this with different values of n, with different degrees of a polynomial. The general scheme is that a polynomial of degree n will have the same integral as a polynomial of higher degree up to degree 2n plus 1, as long as the two polynomials agree at sample points which correspond to the roots of the Legendre polynomial of degree n plus 1. Okay, so if you want to form a polynomial of degree n that will have the same integral as a higher degree polynomial, you just make sure that the polynomial g copies the values of the higher degree polynomial f at those particular sample points, and the sample points are the roots of Ln plus 1, right? Legendre polynomial of the next higher degree. And so that's one thing, that a polynomial of degree 2n plus 1 will actually have the same integral as a polynomial of a smaller degree. So we can simplify the problem that way. We can reduce to a polynomial of a smaller degree. Furthermore, that polynomial of smaller degree is going to be the interpolation of the original function at these certain sample points, and it's always possible to express the integral of a progressive function. Remember, the progressive function is what you typically get when you interpolate a polynomial, right? It's always possible to express the integral of a progressive function as a linear expression in terms of its interpolated values. Okay, that was quite a mouthful, so I'm gonna do an example that will hopefully make this clearer. But the basic idea is that all we're going to have to do is sample the y values of the function f, right? We're going to take the function f, we're going to sample it at a couple points, and then we'll be able to just evaluate a linear function of those several different y values, and that'll give us the value of the integral, right? So it's a simple linear function that we can use to actually evaluate the entire integral. Okay, let me do an example. Hopefully this will make things a little, well, it's a little messy, but hopefully it'll also make things a little bit clearer. I'm going to do the next case up. I just did the case when n equals 1, right? So looking at this general rule here, we have done the case when n equals 1. In that case, g was a linear polynomial, a linear function. And in that case, there were Ln plus 1 was L2. It had 2 roots. So we took 2 sample points, and we were able to get a linear function that has the same integral as a polynomial up to degree 2n plus 1, which would be 3, right? Now I'm going to do it for the case when n equals 2. So this is going to be a bit messier, but hopefully it'll also make this whole thing a little bit more concrete when I work through an example. So I'm going to do it with n equals 2. So that means that the sample points that we're going to use, oops, what have I done? That means that the sample points we're going to use will correspond to the roots of L3, the third degree Legendre polynomial. So if you look back in your notes, you can see that the third degree Legendre polynomial was a constant times 5x cubed minus 3x. And therefore, it's easy enough to determine the roots here. It's obviously got one root at 0 because both of these terms have an x in them. It's also got a root at negative radical 3 over 5 and at positive radical 3 over the 5. So I'll call those 3 points x0, x1, x2. Right? Those are going to be the 3 sample points where we're going to want to sample our function. By the way, since n is equal to 2, if this all works out right, we'll be able to, we'll get a formula to evaluate integrals of polynomials up to degree 2 times 2 plus 1, up to degree 5, right? So this will give us a formula for integrating polynomials up to degree 5. And it will do that, the formula will involve sampling the original polynomial only at these 3 points, at these 3 points. And that'll be enough to tell us what the whole integral will be. Okay, now remember that the scheme is that we sample the original polynomial at these 3 points, and then we form the interpolating polynomial with those 3 points, right? So let's suppose that y0, y1, and y2 are the corresponding values of the original function at those 3 points, right? So y0, y1, y2, those are the values of f at x0, x1, x2, respectively. Now remember how you form the interpolating polynomial. We have to find the coefficients of the progressive polynomial, right? And remember the scheme we had for doing that was to start off with a vector that consists of the 3 y values. And then we remember what we do is we take y1 minus y0 divided by x1 minus x0, right? So that's this. And we also take y2 minus y0 over x2 minus x0, so that's this, right? The first y value remains the same. Okay, so I did the algebra, and it came out to be this, right? If you plug everything in, you can simplify the expressions. You get y0 remains the same, but the second entry is now radical 5/3 times y1 minus y0, and 1/2 radical 5/3 times y2 minus y0. Now we have to do this, we have to iterate this procedure one more time. Now we have to take this value minus this value and divide by this value minus this value, right? So I did the work over here. Let me do that again. I took this value here minus this value here, worked out the algebra, and I got this. And then we take that, which I copied over here, and we divide by this x value, x2 minus x0, which is simply radical 3/5, so that's this. Once again, I simplified everything, and it wasn't too bad in the end. It's y0 times radical 5/3 times y1 minus y0. This second thing simplifies a bit. We get rid of the radical. That's nice. We get 5/6 times y0 minus 2y1 plus y2. Okay, and those are the values of the coefficients, right? Remember, the coefficients are going to be C1, C0, C1, C2. They're the coefficients in the progressive polynomial. So this is a general formula for how to assemble the progressive polynomial if you're given the y values, right? Okay, so again, here are the coefficients of the progressive polynomial. And the progressive polynomial would look like this. Let's see, the C0 is the constant term. C1 is the coefficient of the term that involves the first sample point, which was negative radical 3/5. So it's going to be C1 times x minus negative radical 3/5, so x plus radical 3/5. C2 is the coefficient of the next term in the progressive polynomial, and that has the first factor copied from here, x plus radical 3/5, times x minus the next sample point, which would be 0, so x minus 0. So that is the progressive polynomial, and then what I want to do finally is get a formula for the integral of this progressive polynomial as we integrate from -1 to 1. So remember, integrating from -1 to 1, if you're integrating powers of x, is pretty easy to do. Negative powers of x have integrals which cancel. They just come out to 0. And non-negative powers are pretty simple. You multiply by 2 and divide by the next higher power of x. So let me go through that. C0, the integral of C0, well, that's just a constant, so we just multiply it by the length of the integral. We get 2 times C0. Now, over here, let's see. We've got C1 times x, and we've also got C1 times radical 3/5. Well, the C1 times x, that's an odd power of x, so the integral of that is going to be 0. So, in fact, when we do the integral, we can ignore the x, because that integral is just going to be 0, and we just integrate C1 times radical 3/5, and that gives us this. It's simply 2 times radical 3/5 times C1. Just like the first one, we just multiplied by 2. Now, over here, let's see, we've got C2 times x plus something times x. If you look at this term with the 3/5 here, the only way that's going to figure in the product, you're going to get C2 times 3/5 times x. That would be a first power x term, and that's also going to disappear. So in fact, once again, we can kind of ignore the 3/5. That's not going to contribute anything to the answer, to the integral. And we can simply say, this last term we can simply say is going to be C2 times x, C2x squared. So the antiderivative is x cubed over 3, and you double it because we're evaluating at 1 and -1, so the last term has the integral 2c2 over 3. Okay, so that wasn't too bad. And now what I'm going to do is I'm going to plug in the y values for the c values. So I'm going to replace these c values with their equivalent y expression. So 2c0, well, c0 is just y0, so that's easy. 2 times radical 3/5 times c1, well, c1 was equal to this, right? And 2/3 times c2, well, 2/3 times c2, c2 is equal to this. I did the algebra for you. If you just add up like terms, the y0, the y1, and the y2, you get this. And so this simple expression, pretty simple, right? 5 nines times y0 times plus 8 nines times y1 plus 5 nines times y2. This will give you the correct value of the integral for any polynomial up to degree 3, as long as you you take the y values at those 3 specified sample points. I have rewritten this slightly differently down here. I wrote it as 2, which is the length of the integral, the length of the interval, times the weighted average of the function f at the 3 points. So y0, remember, was the value of f at -3/5, and we're weighting that by 5/18. Y1 was the value of f at the second test point, which was 0, and we're weighting that 8/18. And then y2 was f at the third test point, radical 3 over 5, and we're weighting that 5/18. So we can see that the integral is equal to the length of the interval 2 plus this weighted average of those three different y values, right? Notice that the weights, 5/18, 8/18, and 5/18, they add up to 1 as proper weights should do, right? If you're taking a weighted average of something, your weights should add up to 1. Okay, let's try this out now. Right? Now we've got a new formula. This should work for polynomials up to degree 5, and we should be able to evaluate integrals of polynomials up to degree 5 just by looking at these three sample points. So let's try this example. Let's try the function x to the 5th minus 2x squared. Okay, it's a pretty simple 5th degree polynomial, right? So according to the I'm going to take the integral from -1 to 1 again. So I'm still working on that special interval from -1 to 1. So according to the formula on the previous page, I have to evaluate it at these 3 points, right? Let's see. So I got to do this. I got to evaluate it at -3/5 at 0 and at negative radical 3/5 at 0 and at positive radical 3/5. Okay, so let's do that. Well, this is a little unpleasant, but not too bad. If you plug in radical 3/5 for x, then x to the 5th minus 2x squared becomes this expression. Negative 9 over 25 times radical 3 over radical 5 minus 6/5, not too bad. F of 0 is just equal to 0, right? F of radical 3/5, well, then you get pretty much the same thing we got when we plugged in negative radical 3/5, except that the first term is positive. That's the only difference between these two. And now when you take the weighted average of these three values, right, what did I say? It's going to be 5/18 this plus 8/18 this. What have I done? 8/18 this plus 5/18 this. If you take that weighted average, actually you're going to get some cancellations, like this term is going to cancel against this term. So the whole thing actually just reduces to this. And finally you get -4/3 as the value of the integral. Well, that's pretty neat because we managed to integrate a 5th degree polynomial simply by evaluating it at 3 different points, right? And taking a weighted average of those points. Right, okay. And by the way, you can check this. So I checked it down here by integrating the old-fashioned way, the way they taught you to do it in M211, right? Take the antiderivative x to the 5th into x squared and plug in the limits, and you do indeed get -4/3. So we got the correct answer. Now, let me remove the restriction on the bounds, the limits of integration. Let's suppose we want to integrate from any lower limit to any upper limit. So let's try integrating the same function, x to the 5th minus 2x squared, but this time from 2 to 6. Okay, so how do we remove the limitation on integrating from -1 to 1? Well, we use the same trick I used before, that you think of everything in terms of the midpoint and the radius of the interval. So in this case, if we're going from 2 to 6, the midpoint is 4 and the radius is 2. Right? And therefore, the 3 sample points are going to be, let's see, well, actually the easiest one to start with would be the midpoint. The midpoint is one of the sample points, so that would be 4. That will be one of the sample points. And the other sample points will be one on each side of the midpoint. So one will be 4 minus radical 3/5 times 2, right? This factor, radical 3/5, comes from the root of the 3rd degree Legendre polynomial, right? So one sample point is 4 minus radical 3/5 times the radius, and the other sample point is 4 plus radical 3/5 times the radius. Now this is getting pretty messy, so I would suggest that if you don't believe me, and maybe you shouldn't, if you don't trust me, you probably shouldn't, why don't you try it out on MATLAB and see if it works out. So the formula would say we take the length of the interval, which is 4, times the weighted average of those 3 values of the function, right? The values of the function evaluated at those 3 different sample points, right? And see if you can verify that this value matches the value you would get, again, by integrating the way they taught you in 211, right? Just by finding the antiderivative and plugging in the limits and taking the differences. So if I did all this correctly, you should get the same answer here that you get up here, right? Exactly the same answer. I think I must have tried that out on Mathematica when I first did this, but it's been a couple months since I first went through this section. So I think that's correct. Now, at this point, you might be asking yourself, and well, you might be asking yourself, what's the advantage? I mean, it seems like doing it this way with the Gaussian quadrature, right, using these sample points and then finding the weighted average and all that, that was actually more work than just doing it the old-fashioned way using antiderivatives. Well, you're kind of right about that. This is not a difficult problem to do symbolically, right, using antiderivatives. But remember, this course is in numerical analysis. And so the point is that the application, we're going, I'm sorry, I accidentally hit the scroll wheel. The application we're going to use is what happens if we have an integral that we cannot do symbolically. It's too difficult to do symbolically. For example, suppose you have a function like, or rather an integral like integral from 0 to 10 of e to the sine 2x dx, right? That is not an easy integral to do. I bet you didn't do anything like that in 211, 212, 311, or 312, right? You probably never did one quite like that. So this is not an an elementary problem. You probably would want to evaluate this one numerically. Now, you could, of course, evaluate it numerically using the trapezoid method or the Simpson method, using one of those MATLAB functions we wrote earlier. And in fact, if you do that, you'll find that the integral turns out to be, I think this is accurate to 6 significant digits, 12.9295, right? So I did the integral numerically using our earlier methods and came up with that. But now let me show you how you could estimate the value of the integral using Gaussian quadrature. Now, in order to justify this, we have to assume that this function, e to the sine 2x, although it's not a polynomial, we have to assume that it's not too different from a polynomial. We have to assume that it would be possible to approximate this function pretty well with a polynomial of degree no higher than 5. Now that may or may not be true. We'll see how true it is in a minute, actually. But it's frequently a safe assumption that a polynomial, even if it's not, an arbitrary function, even though it's not a polynomial, it's usually safe to assume that it can be approximated pretty well by a polynomial of a sufficiently high degree, at least on a finite interval, right? If you have a finite interval like this from 0 to 10, it should be possible to approximate the function to a high degree of accuracy using a polynomial. Now, we may not be able to do it with a polynomial of degree 5, but you may have to use a higher degree polynomial. But for the purposes of this example, I'm going to assume that we're just trying to approximate it with a polynomial of degree 5 because that's what we have the formula for. So assuming that this function is similar to a polynomial of degree 5, we can apply the Gaussian quadrature formula we got on the on this previous page. Where was it? This one. Yeah. No. That one. Oh, yeah. What we did here, right? Basically, right? We're going to take the average on the weighted average of the function at these 3 points, right? So we'll apply that to this function. So this interval goes from 0 to 10. So the mean is 5, the midpoint is 5, and the radius of the interval is also 5. So that means the first test point will be at 5 minus radical 3/5 times 5. That reduces to 5 minus radical 15. The midpoint is 5. That'll be another test point. And the third test point will be at 5 plus radical 15, right, on the opposite side of the midpoint. Now, once again, what we now do is we form the Gaussian quadrature expression, we multiply the length of the interval, which is 10, times the weighted average of the function at these three values, at the three x values listed here. And we weight them according to the weights we've used previously, 5/18 for the endpoints and 8/18 for the midpoint. And I worked this out with MATLAB, and it came out to be 12.4020. Okay, that's not so good, right? It's not even quite accurate to two significant digits, right? It's really only accurate to one significant digit, but nevertheless, it's not that bad when you consider that we only use 3 sample points, right? We tried to approximate this integral by only looking at three points, evaluating the function at 3 sample points, right? Simply looking at 3 sample points was enough to get this value for the integral. And when you compare it with the true value, that's not bad for just 3 points, right? For comparison, recall that if you want to use the trapezoid method to approximate this integral, you're probably going to have to use thousands of sample points, right? You would probably want to break the domain up into thousands of subdivisions, right? And you'd take a sample at each one of the subdivisions. So you'd have thousands of sample points for the trapezoid method. Even for the Simpson's method, you'd probably have to do 40 or 50 subdivisions in order to get a good estimate, right? So considering that we only use 3 sample points, we got a pretty decent estimate, right, as compared with having to do it with 50 or 100 with Simpson's method or 1,000 with trapezoid method. That shows how powerful this method can be. And if you're willing to use more sample points, right, if you're willing to use maybe 10 or 20 sample points, you can get much better estimates, and maybe in some cases more efficiently than even using Simpson's method. So that's the real use of Gaussian quadrature in numerical analysis, is that it provides another method for getting for numerically approximating difficult integrals, right? And in some cases, as long as the function is not too eccentric, as long as it's pretty well behaved, it's can be well approximated by a polynomial of degree that's not too high, then this is actually a good method for evaluating an integral. Okay, let me point out one last thing. I used the Legendre polynomials, the theory of Legendre polynomials, to persuade you that Gaussian quadrature is possible, right? That it's possible to find sample values, x0, x1, x2, up to xn, and weights, like in the previous case, the weights were 5/18, 8/18, and 5/18, right? It was possible to find sample points and weights that would allow you to calculate the value of an integral for polynomials up to a certain degree, right? But now that we know that that's possible, there are other ways to determine those sample points and the weights. So I'm going to follow the book here. Suppose I'm going to use this notation, I of f is equal to the integral from a to b of f. Now, for what follows, a and b are going to be fixed, right? We're going to be looking for integrals over a particular domain, but f will vary. And also, I should say, n is going to be fixed, so the degree of the polynomial and the number of sample points will be fixed, right, for what follows. What we're going to do is we're going to let f be a power of x. And because the formula that we are going to come up with is supposed to work for any polynomial up to degree 2n plus 1, then in particular, it should work for these functions, for 1, for x squared, for x cubed, x to the 4th, all the powers of x up to x to the 2n plus 1. It should give us the correct value for those for the integrals of those functions on the interval from a to b. Now remember, the way the scheme is going to work is that we're going to take the length of the interval, which is b minus a. We're going to sample f at these various points. So we're going to take the value of f at x0, the value of f at x1, at x2, and so on, all the way up to the value of f at xn. So we're going to have n plus 1 sample points, right? The index goes from 0 to n. And each y value or f value will be weighted by a corresponding weight. So w0, w1 up to wn, right? And we take the average value of the function at those sample points and multiply by the length of the interval, and that is supposed to give us the value of the integral, right? So that's supposed to give us the exact value of the integral. That should be an exact equality for all of these functions, right, up to power 2n plus 1. So if you think about it, what is that? What have you got? If you write out an equation like this, for all the cases as the powers of x go from x to the 0 up to x to the 2n plus 1, what we end up with is we get 2n plus 2 equations, right? The powers go from 0 to 2n plus 1, so that's 2n plus 2 equations. How many variables are there? Well, the x variables go from x0, x1 up to xn, so there's n plus 1 x variables. And same thing with the w values. The w values also go from w0, w1 up to wn, so there's also n plus 1 w values, so that means the total number of variables is 2 times n plus 1. So that's good, right? We have 2n plus 2 equations in the same number of variables, right? Same number of variables as equations, so we should be able to solve the system and figure out what the x's are and what the weights w are. The trouble is, these are nonlinear equations, so we cannot solve these using row reduction or something, right? This is going to be pretty nasty to solve. Let me show you a really simple example of doing this. Let's go back to the case n equals 1, which we did early on in this lecture, right? Remember, when n equals 1, that means we're going to be approximating a function with a linear interpolation, and we're going to be sampling the function at only 2 points, right? So we're going to have 2 sample points, x0 and x1. So furthermore, let's assume that the limits of integration are just the standard ones, -1 and 1, right? We're going from -1 to 1. Now, because n is 1, we're supposed to get the correct answer for any power of x from x to the 0 up to x to the 3rd power, 2n plus 1. So we should get the exact value of the integrals for all of these functions, right? f of x equals 1 equals x squared equals x cubed. And in each case, the value of the integral is supposed to be given using this Gaussian quadrature scheme, right, where we multiply the length of the interval, which in this case is 2, times the weight of the first sample point times the value of the function at the first sample point plus the weight of the second sample point times the value of the function at the second sample point, right? In the case when f of x equals x, f is just the identity function, so the y value is the same as the x value, right? So x0 is also y0 in this case, and x1 is also y1. And in this particular case, when f of x equals x, the integral of the function from -1 to 1 is actually just 0, right? Because that's an odd degree polynomial, so the integral is going to be 0 on this domain from -1 to 1. So therefore, we get this equation, right? Let's see. So we get this equation. W0 and x0 and w1 and x1, they have to satisfy this relationship. And now you repeat this for all the other functions of f. So for example, when f of x equals 1, then the integral of f of x from -1 to 1 is simply 2, and that should be equal to this. The weight w0 times the value at x0. This is a constant function. It's always equal to 1, so the value of the function x0 is 1, and the value of the function x1 is 1. Right? So we get this equation, and I think you're probably getting pretty fed up with this. So let me just go quickly through this. The integral of x squared from 1 to 1 is 2/3. The integral of x cubed from -1 to 1 is 0. So you get these equations, therefore, also. So in the end, what you get is a system of 4 equations in 4 variables. variables are w0, w1, x0, and x1. And these are the equations that we get from looking at the cases where the function is any power of x from 0 to 3. So, by solving this system of 4 equations and 4 variables, you should be able to figure out what x0, x1, w0, and w1 are. In fact, you should discover what we found earlier, which is that x0 and x1 are actually plus or minus 1 over radical 3. Remember, that's what we found earlier when we did the linear interpolation. And that the weights are equal, that they're each equal to 1/2, right? We simply take the average of the two y values. So that's what you should find when you solve this system. But okay, this is another way to do it, and in some ways maybe it's more elementary because at least you don't have to use the theory of Legendre polynomials. But I'm going to leave it at that. Okay.